In section 9.1, we're going to cover linear and nonlinear systems of equations. A solution to a system of two equations in two variables, say x and y, is an ordered pair x comma y that simultaneously satisfies both equations. So in the particular case that we're going to be looking at in this chapter, we're going to have two equations, and usually that's what's going to denote our system, and we tend to put them in like a bracket or a brace notation to let everybody know that we're considering both of these equations simultaneously. And notice that in either one of the equations that we have, we're working with two variables. In this case, the x and the y variable. So to have a solution to the system, what we need is for an ordered pair to satisfy both equations at the same time. For example, with the given system, x minus 4y equals to negative 11, and x plus 3y equals to 3, let's check to see whether the ordered pair 1, 0 is a solution to that system. So just like back in the basics, if you wanted to check whether or not it's a solution, we have to plug the values of the variable into the equation. And in this case, equations. Everywhere we see an x, I'm going to put a 1. Everywhere we see a y, we're going to put a 0. And we want to see if it leaves both equations true. The second one was 1 plus 3 times 0 equals to 3. And this results in the following statement. We get that 1 equals to negative 11 and 1 equals to positive 3. So we plugged it in, and neither one of them actually ends up being true. But in particular, because both aren't true at the same time, we would say that the ordered pair 1, 0 is not a solution to the system. Let's try another ordered pair. Let's try the ordered pair 2, 5. So I'm going to plug that in. So everywhere I see an x, I'm going to put a 2. Everywhere we see a y, I'm going to put a 5. This would look like 2 minus 4 times 5 equals negative 11. And 2 plus 3 times 5 equals to 3. If we use order of operations on the first one, 4 times 5 is 20. 2 minus 20 is negative 18. And on the bottom one, 3 times 5 is 15, plus 2 will give us 17. So once again, this is not going to be a solution because both equations are not true at the same time. So that ordered pair 2, 5 is not a solution to the system. Let's try one more. Let's check to see whether the ordered pair negative 3, 2 is a solution. Everywhere we have an x, we're going to put negative 3. Everywhere we have a y, we're going to put positive 2. And let's see. Negative 4 minus 2 is a negative 8. Combining it with a negative 3 will give us negative 11. So the first equation does check out. So negative 3, 2 would be at least a solution to this equation. However, to be a solution to the system in total, it has to satisfy both equations. Let's check the bottom one. Positive 3 times 2 is 6. 6 plus a negative 3 is a positive 3. And so we look at this, and it is true. By plugging negative 3, 2 into the system, both equations are satisfied simultaneously. And so the conclusion would be we can say that the ordered pair 3, 2 is a solution to the system. The next question is something that we're going to kind of lead into. So we found one solution to the system. It's worth asking the question, are there any others? Or what potential types of solutions can a 2x2 linear system have? And to kind of answer that, let's think about what this solution means. Okay? If you look at this first equation, so some of us might recognize this, it's the standard form of a line. Instead of being in y equals mx plus b form, this is in the form ax plus by equals to a number c. This is the general form of a line. It's a form that usually you don't see it in too much. Up to this point, typically whenever you're given a line, you're almost always taught to put it in y equals mx plus b form. But what this is the general form of a line. Okay. So if I were to graph this, so let's suppose we have a graph right here. We know that its graph is going to end up being some kind of straight line like this. If we have a 2 by 2 system, so we're going to have a second line like this. Let me call it dx plus ey equals to f. So there's going to be some second line that's going to be a part of our system. Maybe I'll graph it in green. And now let's think about for a moment what a solution to each one of those equations individually would mean. Okay, so to be on the orange line, okay, those ordered pairs x comma y would have to satisfy the first equation. The ordered pairs that are going to be on the green line, x comma y, have to be solutions of the second equation. Now, if we think about what does it mean to be a solution to the system, to have a point x comma y that's a solution to the system, that means that it has to satisfy the first equation, which means that it has to be on the graph of the first line, and it has to satisfy the second equation, which means that it also has to be on the graph of the second line. So geometrically, those points that are solutions to the system are going to be on the intersection of your two lines. Okay, so if an ordered pair x comma y is a solution to the system, those ordered pairs are on the intersection of the line. So if it's a solution to the system, then it's going to be on the intersection of the two lines. Now, qualitatively, this will allow us to kind of answer that previous question in terms of what kinds of solutions can we get. If you think of the qualitatively three different ways that lines can position themselves, you have a situation kind of like what we saw here in a minute, where it's possible that maybe you have just a single point of intersection, like this. That's exactly what we saw in the first example. Even though we didn't necessarily verify it or prove it all the way out, this particular system will have just exactly one solution. On the other hand, we know that it's possible to have lines that coincide, and that's where the two lines lie right on top of each other. So that's one solution. If the two lines coincide, then any point on one line is also another point on the other line. And so in this case, we're going to have infinitely many solutions. If I could spell infinitely. And in the last case is if we have a pair of non-intersecting parallel lines, those two will never cross each other. So there would be no points that would be simultaneously on both lines. This would be an example of a system that would have no solution. And these are the three different cases you will see with 2 by 2 linear systems. Systems will either have exactly one solution, or infinitely many solutions, or it's possible to have no solution. The first method we're going to discuss on solving these is what's referred to as the substitution method. Under the substitution method, what we want to do is solve one of the equations for one of the variables. It doesn't matter which equation you pick or which variable you choose to solve for. Generally speaking, you want to choose the one that's kind of the easiest. If there's one variable that you notice in particular that you can get by itself very easily, usually without having to introduce fractions, that's the one that you want to go with. You will then take the equation that you found in the first step and substitute it into the second equation in your expression. This will result in a single equation that has one variable in it. we will go ahead and be able to solve that equation for the one variable, and then we will take that value of the variable, plug it into one of the previous expressions in order to find the value of the other variable. So let's take a look here. In example A, we want to solve the system 2x plus y equals to 6 and negative x plus y equals to 0. So what I want to do is I want to find one of these equations where I can very easily get a variable by itself. And if I look at the second equation in particular, I can really easily get the y by itself. If I have negative x plus y equals to 0, if I simply go ahead and add x to both sides, that second equation would then tell us that y equals to x. Again, this is just how I choose to do this one. There's no wrong way to do this one. You could either solve the second equation for x even instead of y, or you could solve the first equation for y. So there's more than one way to go about this. If the work you have might be different from that of a classmate or somebody else, it doesn't mean that it's wrong. You just might have chosen a different equation or a different variable to solve for. But as long as your algebra is good, you don't make any mistakes, we will all come to the same conclusion. So here's what we came to right now. And I'm going to just change the color here for a minute to highlight this. We have y equals to x, and this is coming from the second equation. Let me recopy down now the other equation. So I'm going to copy down the first one. And notice what this says is it says that 2x plus y equals to 6. What we can do is use the expression for y that we just found in the other equation to substitute it in. Because we know that y is equal to x from the second equation, what I can do is everywhere I see a y in the first equation, I can simply replace that with x. And this is good for us because once you do that substitution, notice that this equation right here that we formed now has just a single variable. It only involves the variable x. I can now go ahead and solve for x. 2x plus x equals 3x equals to 6. Divide both sides by 3, and we get x equals to 2. Okay. So far, so good. Remember, a solution to a system, though, isn't just a value of x or y. It has to be an ordered pair. Now that we know the value for x, we can plug that into our substitution equation to find the value for y. We know that y is equal to x. So if x equals to 2, that means that y also equals to 2. So this gives us our solution. Our ordered pair is going to be 2, 2. And please make sure that whenever you're solving systems, you want to write your solutions as ordered pairs. One of the beautiful things about algebra is, again, if you have a solution, we can check this if you want to, just to make sure that we got it right. Let me plug 2, 2 back into the original to show that we get a true statement. So everywhere I see an x, I'm going to put 2. Everywhere we have a y, I'm going to put 2. This is 2 times 2 plus 2 equals to 6. Negative 2 plus 2 equals to 0. 2 times 2 is 4, plus 2 is 6. So we get 6 equals to 6. And in the second one, we get negative 2 plus 2, which is 0. And so we get 0 equals to 0. So plugging that ordered pair in, it satisfies both equations simultaneously. So that proves that 2, 2 is a solution to our system. Let's take a look at another one of these. We have x minus y equals to negative 4. And we have x squared minus y equals to negative 2. So we want to pick one equation and solve it for one of the two variables. There's a lot of different ways you can go with this one. Maybe I'll take the first equation and solve it for y. Actually, I don't know. Let's solve the first one for x. There's no wrong way to do this. It's just kind of like what you're feeling like doing. I'm going to get the x by itself. So I'm going to add y to both sides. This will give us x equals y minus 4. So this is coming from the first equation. and I now have x by itself. X is equal to y minus 4. Once you've solved that variable for one equation, we now turn our attention to the other equation in the system that we didn't use. That is x squared minus y equals to negative 2. And now we know that we already have an expression for x from that previous one. We know that x is equal to y minus 4. So anywhere we had an x in that second equation, we can replace that with y minus 4. And again, at the end of the day, this is the goal. This is what we were hoping for. We've now created a situation where we have one equation with just one variable, namely the variable y. Let's go ahead and try to solve this for y. Notice that we have a square here. So we want to get rid of that parenthesis by distributing. If I do the distribution property, or FOIL as some of you call it, that's going to be y squared minus 8y plus 16 minus y equals to negative 2. Can combine some like terms here. Negative 8y minus y is negative 9y plus 16 equals to negative 2. And now the next thing we can do to get one side to be 0, because we do have a quadratic, notice that it's the variable y squared. We're going to go ahead and add 2 to both sides. This produces y squared minus 9y plus 18 equals to 0. To solve this quadratic, you should want to try to factor it. If you're unable to factor it, you can always use the quadratic formula. Fortunately, this one will factor as y minus 3 times y minus 6 equals to 0. Set each factor equal to 0 independently. We get y equals to 3 and y equals to 6. So we're going to have two solutions to this one, which I'll explain in a minute. One is going to have a y value of 3. One is going to have a y value of 6. To find the corresponding x values, this is where you go back to your substitution equation. If x equals y minus 4, then when y is 3, x is going to be 3 minus 4, which is negative 1. And if y is equal to 6, then x is going to be 6 minus 4, which would be 2. So we have two solutions to this system. They are negative 1, 3 and 2, 6. It's worth asking the question that we just said a moment ago. We get one solution, no solution, or infinitely many solutions. How can we get two solutions like this? And well, the answer is, if you look at the second equation, this one wasn't linear. This was x squared minus y equals to negative 2. And we know that the graph of an x squared term, remember, that's a parabola. If you're talking about what are the solutions like when it comes to a parabola, and this top one, which is a line intersecting, that can happen a couple of different ways. You can get two solutions, as we have here, where the line and the parabola intersect like this. You could have exactly one solution if the line intersects the parabola at just the vertex, or it's even possible to have no solutions if the line and the parabola don't intersect at all. Okay. So only for the linear systems, when both of your equations are lines, do you get either one infinitely or no solution. Here we actually had a nonlinear system, and the reason why it was nonlinear was because of that x squared term. But the steps are still the same. You use the substitution method, solve one equation for one variable, take that expression, substitute it into the other equation to reduce it to a single equation of one variable, solve that, and then back substitute via your substitution equation to find the value of the other variable. And then last but not least, please make sure you're writing your solutions as ordered pairs. Let's take a look at the next one. We we have x minus y equals to 2, and 6x minus 5y equals to 16. Looking at this system, I kind of see the first equation, and I look at it and I say, well, that's probably pretty easy to get the x by itself, so I'm going to do that. I'm going to take the first equation. To get x by itself, I'm going to add y to both sides. This cancels. So we get x equals y plus 2 on that right-hand side. We're now going to turn our attention to the other equation. It's 6x minus 5y equals to 16. And we know what x is. Everywhere we see an x in that second equation, I can replace it with the expression y plus 2. So it's going to look like this. This now gives us a single equation in the variable y. We can go ahead and solve this. To begin, let's distribute to get rid of the parenthesis. We have 6y plus 12 minus 5y equals to 16. On the left-hand side, like term 6y minus 5y cancel to give us y. So we have y plus 12 equals 16. Subtract 12 from both sides, and we get y is equal to 4. So we now know our value for y. We can find the value for x by plugging it into that substitution equation. If x equals y plus 2, then x is going to be 4 plus 2, which means x equals to 6. So let's write out our solution. Again, be very careful. These are ordered pairs. X comes first and then y. So the solution is 6, 4. Let's take a look at one more. This is part D. We have 6x plus 5y equals to negative 3. And on the second one, we have negative x minus 5/6y equals to negative 7. In this one, there's a pretty clear-cut winner in terms of what to get by itself, and that's going to be the x in the second equation. The reason why I say that is that one we can get by itself without having to divide by any kind of coefficients or introduce more fractions than what's already there. Like, for example, if you look at the x in the first equation, to get the x by itself, at some point you'd have to divide by 6, which would create additional fractions. Similarly, if you try to get the y by itself in the first equation, then you'd have to divide by 5 at some point, which would, again, introduce more fractions. And then for the y in the second equation, it already has a fraction of 5/6. In order to get rid of that, you have to, at some point, either divide by 5/6 or equivalently multiply both sides by 6/5 to both sides. However, because the x just has either a coefficient of 1 or negative 1, that should be our best bet. So first things first, to get the x by itself in equation 2, I'm going to add 5/6y to both sides. That gives us negative x equals, on the right-hand side, we have the positive 5/6y, and we also have a negative 7 term. The next step to get x by itself is I want to get rid of that negative 1. You can either divide by negative 1, or equivalently, it's the same thing as multiplying by negative 1. So let's multiply both sides by negative 1. We get x equals, if I distribute on the right-hand side, negative 5/6y plus 7. So x equals negative 5/6y plus 7. So we're now going to take that and we're going to substitute that into the first equation. The first equation is 6x plus 5y equals to negative 3. like this. So everywhere we see an x, we can replace that with negative 5/6 y plus 7. This equation now only has y in it. Let's go ahead and distribute. 6 times negative 5/6 will give us a negative 5y. 6 times 7 is 42, plus 5y equals to negative 3. On the left-hand side, we have like terms we can combine. A negative 5y and a positive 5y cancel, and we're left with 42 equals to negative 3. Of course, that's false. That's a contradiction. And what that means is that regardless of the choice x and y, this system will always boil down to a contradiction, which is a false statement, meaning that there will be no ordered pairs that will satisfy the system. This is an example of a system with no solution. So whenever you do your substitution, if the single equation you result in has all of the variables cancel and you're left with a false statement, that's what a no solution system would look like.